So let's see. I guess I'll share this document too. I figured I would just kind of try to explain what's happening. And we'll kind of take it, I don't know what's the word, just naturally. Go where it goes. So let me get the branch pulled up. Latch target thread 2. Probably the place to start is let's start with where I'll start with what happens when, well, I guess we'll start way back just to make sure we're all on the same page, but real briefly, like the goals I was trying to go through for, right, of, which is basically like when you wake up, right, when a thread is blocked on some other task completing, and that task completes, we want to wake up just that one thread, which somewhat amazingly Rayon doesn't do today. And we want to, when new work arrives, start a relatively small number of workers in response, a proportional number of workers in response or something, and so forth. But basically, Rayon scheduler today is just kind of on-off, and we want to make things more proportional. And we want to do it all by being fast, but I'll leave that out. So the one key thing in the code is this. I'm going to navigate in here. If you look in Rayon core, source, sleep, counters, actually, well, I'll describe the code as it is. I thought of one small change I would probably make as I was reviewing the algorithm, but we can discuss it. This is kind of a key data structure, this atomic counters. This is like a central, it's the central state for the scheduler. And it has 4 things packed into one 64-bit word. And the reason for that is we want to be able to modify them atomically all at once. So one is the idle, or the easiest ones to explain are the idle and sleeping threads. And basically, what this is counting is just the number of threads. An idle thread is one that is blocked on some latch and looking for work. And a sleeping thread is one that is asleep. And actually, in this case, idle is a superset of sleeping, at least in the data structure. That doesn't have to be that way now, but it just is. So in other words, we increment, your thread kind of increments the counter when it goes idle, and then if it goes to sleep, it increments the sleeping thread, but it doesn't decrement the idle until it finds work. So incremented when you are searching for work, decremented when you find it, incremented when you go to sleep. We'll talk about that process. Decremented. And one minor detail is that when you go to thread, well, we'll see this later, but when you go to sleep, you increment this counter that says you're asleep. And when you get woken up, the only way to wake up from being asleep is somebody else wakes you. So when you get waken up, the one that wakes you decrements the counter. That's a total, probably irrelevant micro-optimization to keep the counter just a little bit faster and more in sync with who's waking up. Does that make sense so far?
I guess.
Okay, so the last part of these 2 words, the jobs and sleepy counters, and they're basically a mechanism for detecting when new work is published in a lightweight way. I'll I'll cover them in a bit, but the high level idea is that the sleepy counter gets incremented when a thread gets sleepy, which means it's planning to go to sleep, but it hasn't yet. It's going to search one more time or so before it does. And the jobs counter gets synchronized with the sleepy counter. So that means it becomes when new work is published. So the idea might be this: if the jobs and sleepy counter are equal, then nobody has tried to go to sleep since work was made available. And so there's no work that gets done. But if someone says that they're sleepy, then when we make new work, we'll increase the jobs counter to match. So if the two counters are equal, nobody has gotten sleepy. We'll come back to this since work was published. But if they are not, when new work is published, they are made equal. Okay. So these are kind of the key. So that's one of the key data structures. The other one is here in sleep mod. So the worker sleep states. Which is basically an array. For every worker, it has a mutex. And a Boolean that is false, that is set to true when the worker goes to sleep. We'll come back to that. And set to false when the worker is woken up. So this is a way, we used to not have per worker states, but having a mutex per worker means that if you want to wake up a specific worker, you can do that. Versus very easily, and if two workers are being woken up, they don't contend with one another as well. And is there anything else? I guess the latches. So let's see, latch. So for latches, a latch in Rayon terminology, which I don't know if other people use this or if I just made it up, I can't remember, is probably somebody uses it, I hope. A one-time event, basically. So sort of like a barrier, but it won't be happening multiple times. So it's not set, and then it gets set. And when it's set, then something has happened that's interesting. And so the latches basically go from unset to set. And each latch is created by some thread that is waiting for that event. And there are various kinds of latches. They all wrap a core latch, more or less. So the core latch is just a wrapper around an atomic U size. It has 4 states. We'll talk about them in a little bit, but unset, sleepy, sleeping, and set that are used to track what's happening. So unset means the event has not happened, and the owning thread is awake. Sleepy means the owning thread is going to sleep, but hasn't yet. Sleeping, the owning thread is blocked and must be awoken when the latch is set. And set means the latch has been set. Event has happened. So the idea is when you come to set the lock, you can kind of, if it's unset, you don't have to do anything, but if it's in one of these 2 other states, you might have something you have to do, especially sleeping. So those are the data structures. Let's see.
I do have a quick question before we forget. You're using atomic U64, which is not supported by all targets. How do we feel about that?
It's a good point. I don't know. I don't care. Maybe I do. We could plausibly, we might be able to get to squeeze into fewer bits, but I'm not sure. Are there any realistic targets that don't support it?
MIPS, 32-bit MIPS,
Okay.
and the thumb I think also does not.
But wait a second. For that kind of tiny architecture, how many threads you're expecting to have?
Well, probably not U16 number threads, but we need to either conditionalize the code for that, or, I mean, we need to decide how we want to deal with that in some way.
Yeah, it seems like we could use fewer bits and be fine. But let's table it. But at minimum, it would, like, the most obvious thing would be that we use 2 to the 8 bits for each one, or 8 bits rather, which is still 256 threads, which is plenty. The jobs and sleepy counters could get fewer potentially, though it might impact. I don't think it actually makes a big difference. We have the rollover is an interesting question we'd want to talk about, and it would make rollover more common, but I don't think rollover is particularly expensive, so it's okay. It's a good catch though.
RISC-32 is another one. So I mean, I think of 32-bit targets, i686 and the main ARM targets do support 64-bit atomics, but
it may also be that 32-bit is faster in some cases. I don't know if that's actually true.
Probably, yeah.
Okay, let's keep going, but come back to that because I think we could switch to 32-bit without too much pain if we're willing to put a lower limit on the number of threads.
Or, I mean, it may be 32-bit for 32-bit ARC targets and let it be 64-bit for others.
Right. So let's keep going into events. By the way, hi. It's Thomas, right? I'm not sure.
Yep. Hey.
You missed some of the data structures, but I think we'll be going back over them, so it's fine.
Keeping going. I did also read the code that did this, so.
Okay. So let's see. We can start with like it's the most complicated, but it's probably the in some ways the main thread is what happens when a thread goes idle. And then I think the other things kind of fit into that. So I think it's probably the best place to start. And so the idea is, if we circle back up to registry, the main routine for this is this wait until, not stopped, but there, is this wait until, which basically says I've got a latch and I'm gonna wait and look for work until the latch is set. And I noticed one minor thing about the definition of idle, which is kind of interesting about wait until, but which is that if you're using join, it doesn't call wait until right away. It first drains the local set of tasks, the local deck, I guess, and then calls wait until, whereas the scope method calls wait until right away, even if local deck has tasks. So it's a slight difference between two. I kind of lean more towards the joins definition of idle. Like, in other words, if you just create a scope and push 2 tasks, then you consider yourself idle even before you've like tried to work through those 2 tasks. Whereas join doesn't consider itself idle until the work it created locally is done, if that makes sense.
So is wait until, does that still try to steal from its own queue?
It does. So it's not, it will do the same thing in terms of, first it will steal from its own queue. The only difference is that the like idle counters get incremented. So it might have a difference. It might cause different behavior in terms of, we'll see later, whether we wake someone from sleep or not. But all the benchmarks that were actually having problems were just doing the join behavior. and not the scope behavior, and that would be the one that I think is more correct. So I don't actually think it's that big a deal.
What's the scope behavior used for in the current code?
What do you mean by use? It's used for scope. Do you mean like which benchmarks use scope, or?
I see. Okay.
Most of the parallel iterators are built on join, but scope is used in some things we care about, like the Firefox servo stuff.
Yeah, Firefox, the TSP benchmark uses scope. And so what does WaitUntil do? So it starts by, it has this first round where it's kind of let's see, I'm going to put out the flow. It's like a long little thing. So step one is it's going to be searching for some number of rounds, and each search is like, this is the thing you were asking, Josh, like it takes a local job first, and then it tries to steal, and then it pops the injected job. And if it finds work, we execute it and go back to step one. Or we leave the idle state, execute it, the work, and go back to step one. So that happens here. So the idle state is represented by this like idle state variable. And it's actually a value kind of that gets consumed and produced and is not copy. So it's like leaning on the type system a tiny bit. While that value is live, you're in the idle state, so to speak. But let's see, arrow idle state. So when you start looking, we're just going to add to the counter to indicate we have an idle thread. That's all that really happens when you call start looking. Maybe step one is enter the idle state. Step two, search. And so each time around, while we search, we're going to call, if we don't find work, we're going to call no work found. And that's going to basically just count how many rounds we've been searching. And at some point it gets to the sleepy state. The sleepy state, what it does, the idea of sleepy is we're going to do one more search, and then we're going to start to actually go to sleep. I don't remember if there's a reason you have to have the sleepy state, but I can't find the function that's getting called. Where is it? No work found.
If I remember correctly, this one had like a scheduler yield in it or something.
What's that? This is the function that announces sleepy. But what it does is it basically reads or increments the sleepy counter. The sleepy counter, and stores the old value. And this is something I would like to change, actually. I won't go into the change I want to make yet, though. But the idea is now we've signaled that if the only effect that incrementing the sleepy counter has, we're going to see later, but it has an effect on when work is published. So step 4 would be search some more. And step 5, okay. If we didn't, when we're done, we call this sleep routine. This is where we do the actual work to figure out how to go to sleep. And so one change that's happened here that I didn't mention explicitly, when we are becoming idle, we pass in the latch that we're waiting on. We didn't used to do this in the old Rayon, but so we know the latch that we're blocked on, so that when that should trigger, it can wake us up. So in step 5, we're going to do a bunch of steps. There's kind of 2 separate synchronization things happening. The first one is that we set the latch to the sleepy state. And I realize now that it's a little confusing because I use sleepy in kind of 2 ways here. But so we're telling the latch that, okay, our thread is getting sleepy, then we acquire our thread's lock, and then we try to set the latch to the sleeping state. And the reason we try is that someone may have signaled the latch in the meantime before we actually acquired our lock, or while we were acquiring our lock. In that case, they would have changed the state to set, because they would have set it. So if the latch was changed, abort falling asleep, basically. Wake up from idle state. So the reason we would wake up is that there's no more reason to block. The thing we were waiting for has happened, we can stop. But if we succeed, then the latch is now in the sleeping state. And that means that the next person who sets the lock, or sets the latch, is going to know they have to actually wake us up. And you have to do it in this kind of 2-phase way, because if you don't, it doesn't work. There might be some other way, but this is how we detect like a race between, why do I need the sleepy state? I do, there's some kind of race that is not immediately obvious to me right now, but that if you were to make sure that, well, you need to know if somebody set it, why do you need to know it?
I guess you don't want a work item to be submitted as the thread is going to sleep, because it won't wake up then.
Yeah, but the work item is coming next. This latch, what it would be I'm going to sleep, and let me see, maybe you don't need it actually, but I feel like you do. I feel like there's an obvious problem and I rediscover it periodically.
If the latch is set to wake up the thread, if you go to sleep, do you just immediately wake up again?
Well, what happens is, we can look at that code. So what happens is when the latch, to wake up the latch, somebody has to call set, right? And what happens when you call set is, let's say it's a spin latch or something. It calls core latch.set. And what that does, the core latch method of set, let's count latch, that's something else. Where is this stupid thing? There it is. It will swap with the set value, and then it will check that the thing is sleeping. So it basically sets the value to set atomically. And what I'm trying to figure out is why we needed the sleeping. I'm not sure. Maybe you don't need it. But in any case, what's going to happen is, when they come in, they're going to set the value to the set constant. And then if you were already in the sleeping state, so if this had happened, then they'll come and wake you. And for sure, what's definitely required is that you acquire the lock before you set it to the sleeping state, because otherwise they might observe this, acquire the lock, wake you up, and you haven't even gotten around to going to sleep yet. So maybe the sleepy state isn't actually required. I'm not sure. Actually, I think I talked about it in the RFC. I'll have to check. But regardless, the point is we get the lock on our thread. We set this thing to sleeping. If that succeeds, we can keep going. Because now we want to check whether, I'm in the wrong file again. I want the sleep file. Now we want to check whether there's been any work published since we got sleepy, basically. And so what we do here is we have this little loop. Actually, I'm going to put a link to just to keep the bits of code lined up. So what we'll do is we'll load the current value of the counters. And we're going to compare whether the sleepy counter as we saw it, like whether the jobs counter has changed since we got sleepy, essentially. Well, so I didn't talk about whether that will happen yet, but the idea is when we publish new work, if the sleepy counter is higher than the jobs counter, we're going to increment it up. So if the jobs counter has changed that we got sleepy, then new work has been published since we got sleepy. So we can return back to step 3, I think. So if we look here, we say, if new work is published, we're going to call wake partly. That just resets our counter back to the sleepy level. And so we'll go become sleepy again. We'll do some searching, and if we don't find work, we'll become sleepy again and keep going.
So is this where it wakes all, like once you add new work, it wakes every thread so it can update these counters and then wake itself partly?
It doesn't wake. This is the newer algorithm, so it never wakes every thread.
Okay, so it's going to like wake the number of additional jobs it needs, like the difference between.
Yeah, this is the code for going to sleep. I'll show you the code for waking up yet, but that's exactly right. Yeah, so when it comes to publish work, if it will wake the number of, it'll try to get an estimate of how many threads it should wake, and then it will wake that number, which is basically, yeah. So the last part is, okay, then we increment the number of sleeping threads. So that's what happens here. And you notice this is conditional, and there's a possible loop that can go back around. The reason is this is sort of an atomic swap thing happening. So we read the counters here, and then we try to atomically increment the sleeping threads. And that means somebody can't, like when we exit this loop, nobody can, if somebody's publishing new work, they either adjusted the jobs counter first, or we adjusted our sleeping threads first. They can't come in between, overlap with one another. So either we knew that new work was posted, or they know that we're asleep. And that's important because otherwise they might fail to wake us up. And that would be bad. So we load the jobs counter C, load of C. So either we see that new work was posted, or the new work, or the people posting the work will see that we are asleep. At least that's my contention. So at that point, we've successfully registered ourselves as asleep. We both marked the latch that we're sleeping, and we marked that we have a sleeping thread. That's the two things we have to do. And then we can actually just set this to true and go to sleep. And when we're done, we wake up. So somebody's going to come and signal us, and we'll see that in a second. So somebody will signal us to wake, then we will wake. And when we wake, we don't have to adjust we kind of undo some of what we did. We set the latch state back to unset, unless it became set in the meantime. We set our counter back to 0. We don't, as it happens, decrement the number of sleeping threads because the other person is already going to do it. And I'll talk about that in a second, but you would otherwise want to do that. Okay, so that's the sleeping procedure. So let's see. So maybe we'll say what happens when, we'll do let's do it when a job is published, because that's the most interesting one. I'm assuming you'll stop me when you have questions, people, but please do. So there's 2 ways jobs can get published. Originally, I had slightly different code at some point in this evolution. Now I don't, so they're wrappers around a common helper. They could probably go away. But the idea is, when new work is coming in, you know the job that posted it, although I don't think that's relevant for anything except debugging logs. you know how many jobs were posted. Usually it's one, but it might be two. And you know whether the queue of jobs for that thread was empty before the job was posted. And that's kind of a heuristic. The idea is if the queue was empty, then there's kind of enough threads active. Well, either we're at the beginning or there are enough threads that they're keeping the queue empty. There's whatever work had been in there got stolen. Whereas if the queue has got stuff waiting in it, then clearly there's not enough threads because they haven't stolen the work you published yet. Well, not clearly, it's a heuristic, but that's the idea. So you know the number of jobs that were created, and you know, was the queue empty? If not, then there are not enough idle threads to steal work. So when this gets called, what do we do? Okay, actually before this is called, something happens. Before new jobs is called, the jobs are pushed to the queue. It's important that they're already in the queue. Otherwise bad things can happen. You might miss them. So what will happen here is we're gonna load the counters. So we know how many sleeping threads and whatever else they are. We check if the jobs counter and the sleeping counter are not equal. And that means that then some thread got sleepy since the last job was posted. And we're going to synchronize them. So what this sync jobs counter does is it just sets them to be equal and does an atomic exchange. And you notice it updates counters with, that might take a few rounds, so it has to read, kind of reread the value. So when we're done, basically when we exit this loop, or when we exit this line, at this point, we have an instantaneous read of counters where we know the number of sleeping threads, etc., or idle sleeping threads, and we have notified any sleepy threads that haven't yet become sleeping, that new work was published, and we did that by setting the jobs counter equal to the sleepy counter. So now we can go look and see, okay, how much work do we have? So if there's nobody asleep, there's nothing for us to do because there's no one, we couldn't even wake anyone up if we wanted to. Otherwise, we look and see if the queue is not empty, then this was some tweaking I did. I don't know how important this is. I tweak these heuristics a lot, but it makes some difference. It's basically, you can kind of tune, this is where we decide how many threads to wake up. You can kind of tune how aggressive you want to be, but it's always a bit of a guessing game. This current heuristic is, it says, okay, if there's stuff piled up in the queue, then I want to lean towards waking more people up because they're not doing a good job at keeping my queue empty. So I look at how many jobs I published and the number of people that are asleep, take the minimum and wake up that many people. Otherwise, my queue is empty, so maybe they're doing a good job. Then I'll look at how many idle threads there are, and I'm going to assume that if there's idle threads, they're going to pick off this. They're going to pick off this job. I don't need to wake up more threads. I already have an idle one who is searching for work, so I'll leave it to them. And so I'll only wake up more threads if there's not enough idle threads to take care of the work that I have.
Now there's an obvious, I mean, I know this is heuristic, but there could be multiple threads trying to do this push at the same time.
Yes,
pushing more than
exactly. So there's a couple ways this can go wrong, right? Or how many threads to wake? Yeah, you only have a sort of partial picture. And I think that was exactly why I added this queue is empty heuristic, was that if there are multiple threads pushing all at the same time, then like,
they don't both get to claim all the sleepers, basically.
Right. Yeah.
Or all the idle threads, I mean. They
can, I mean, sort of, exactly. Over time, they should, it should stop, right? Like your first push before your queue is empty, you push it on and you see an idle thread and you think, okay, great, he's gonna take it. And then your next push, well, it turns out that idle thread got stuck taking somebody else's work that you're not aware of. But on your next push, your job still isn't taken. So now you don't trust the fact that it's idle anymore, and you just go and wake somebody up because something's not right. That was the idea. And I think I did notice, I don't remember, we'll have to rerun, but I think I did notice some of
low, right? It's just, it would happen basically if the idle thread is woken up but has not updated the counters yet, which is possible.
Sorry, what would happen in that case?
So this would only be inaccurate in the case where the thread is woken up but hasn't yet updated the counters.
No. The other problem is that it's not just one thread. There's not just two threads involved. There are many threads, right? So the case that Josh was saying is that like if two of us are posting jobs, it can happen that we both see one idle thread, and each thread thinks I only have one job, so they think it's okay. That idle thread will take my job.
This whole function is basically concurrent, right? This function will be executing on every thread at once.
Yeah, exactly. This is kind of the inherent trade. Like I don't know how you can't get rid of this trade-off. From what I can tell, you can't get a global view, so you have to take a guess of what's happening.
I think the pathological case would be if you don't push again, so you don't see that we changed queue was empty.
Yes, if your jobs are very big, then it matters. Like if you have a few big jobs, it matters a lot more than if you have smaller many jobs, because overlooking one is not great. There is another trick to help with that case, which I will show you in a second.
Okay.
Well, actually, maybe I'll show you right now. So I forgot, I didn't mention it when we were, well, maybe let's take a few notes first of all. So the problem is we have only an isolated picture. It is possible, for example, that two threads will post work. Each thread sees, or when there is only one idle thread, each thread sees one idle thread, decides not to wake anybody, but now we have one thread and two jobs. So there's one other hack to help with that, which I think I found in the Go scheduler, and I thought was pretty darn clever, which is here. When you find work, that means you're transitioning out of idle and into busy. At that point, you decrement the idle counter, but you look, if you were the last idle thread, then you wake up another thread. And the idea is exactly for this case that, okay, maybe two threads came, and so I'm just gonna wake up one more. And if it happens that that thread doesn't find any work, it'll go back to sleep. So you kind of get like a little ripple. But if it happens that you have work waiting, then it's gonna be a smoother transition.
So yeah, that's important then. And it means there's going to be a chain of latency for this to take effect, but it will eventually take effect. And that's
right.
Probably.
There's two things to consider, I guess. So let's see, what happens when you stop being idle? If you are the last idle thread, wake up one more thread just in case. There's like the deadlock condition and then the efficiency condition. And the deadlock condition is that you never want to inject a job and nobody notices, like everybody's asleep. And that I think is impossible. And that's where I kind of emphasize some of these, atomic conditions. But the other case of just you inject a job and people are awake, but not as many as you would like, that's definitely possible. And that's what this is aimed at, reducing that.
So sort of meta comment. I think there are a lot of things that you're bringing up and putting in the document here that are important points or caveats or talking about the interactions that aren't fully reflected in comments in the code. So that needs to be translated over.
That's partly why I'm putting them in the document. I totally agree. Code is the kind of code I, always chide people for submitting in a PR, where a lot of the logic isn't there. But it's exactly what you write when you're just hacking it up. Yeah. So that's right. I'm trying to think. Oh, I guess the last point, we could move on from this, but the last thing I wanted to show you is just the latch code. Well, let me just show you the wake any threads actually before we do anything else. So how does wake any threads actually work? It's not the most efficient, but I don't think it matters. At least I never seen it on any benchmarks. It iterates through all the threads, at least right now, because we don't really have a central list of which ones are asleep. Could probably change that, but we don't. So we just know that there are sleeping threads. We don't know which ones there are. So we iterate through, we acquire, for each one we invoke wake specific thread, which acquires the lock on the thread, checks if it's asleep, and if so, notifies the convar, and this is where I keep referring to. This is what actually does the decrement of the number of sleeping threads. And the reason I put it here, I did comment it in this case, it's a micro optimization. The idea is there's another possible race condition where if you decrement the sleeping thread only when the thread itself actually wakes up and two people are publishing jobs, then one of them might think that there's one of them might think there are more threads that are available to be woken up than there actually are. So the sooner you decrement this counter, the faster you advertise to everybody else who's considering whether to loop through and look for more threads to wake up that in fact there's not anyone to find. It seems to me that this loop is probably okay if you have like 8 or 16 threads. If you had 256 threads, it might start to be a bottleneck, and we might want to replace it with some central vector or some way to know which indices you should wake up. That's kind of annoying to maintain. But.
So, sort of a related point, the thread that wakes up doesn't know who woke it up, right?
No.
So it seems like they're, especially with the higher number of threads, it seems like that's something we could optimize to have it. If it knew who woke it up, it would also know who to go trying to steal from first.
Yeah, that's a good point. So let's see, first searching through all threads to find those that are asleep is not great. And secondly, when a thread wakes, it could be told where the work is waiting for it as a heuristic of where to start searching. Yeah, it wouldn't be like a guarantee because someone else might have stolen it.
Right, but it's.
This actually has, does this have a lock over the, you said it has a lock over the particular thread that it's using, but it still means that that thread could steal from other people, right? It's just the lock for this. Actually, like,
yeah, each thread, this is one of the parts you missed, but each thread, there's a lock, there's something called the worker sleep states. And there's basically a vector of 1 per thread, and they each have a lock. Here it is. That's just recording if they're asleep or not. It's not used for anything else and doesn't affect who they might.
Okay, and that's not set by the worker at all. It's only set by the scheduler level stuff.
Yeah. Yes. The worker. I'm not sure what you mean by set by the worker, but the worker thread in the scheduler code, the worker thread says I didn't find work, and when it's going to sleep, it'll set that to true. And then in this code, when somebody
okay, so I was okay. So the worker thread will grab that new text. Okay.
Yeah, it's kind of a meta scheduling variable. It's not used by user code or visible to user code. All right, so okay, so let's see, back to where we were. Heuristic, how many threads to wake, or the code that does the wake up. I'll just take a, that's this, might as well document what we said. Wake any thread. Yeah, okay. Decrements number of sleepers. Okay. The only other thing I didn't show you is latching, but actually latching's pretty, like that's the way to wake someone up, is setting a latch. We kind of vaguely covered it, and it's pretty simple. It's simple conceptually. There were a few refactorings I had to do along the way, but in order to guarantee this property. But basically, since every latch has, so the idea is, okay, the core latch isn't really exposed very publicly, but it just contains the core machinery of how, like this core latch flag that goes from unset to set, but it doesn't track other stuff like who the owner is. That gets tracked by these outer wrappers that each have a slightly different way. But the spin latch is the most basic one. It keeps a hold of the registry, but also the index. I guess I called it the target worker instead of the owner. But so the idea is when you get set, you're going to go through, you never call the core latch set directly. That's private, but you go through these outer layers, and they'll call this method notify worker latches set, which wound up going down to wake up the specific worker.
Is there a race here between being woken for your latch and being woken for general work? Or
there's a kind of race in that someone could set your latch and wake you up at the same time that that someone else is posting work, and you're considered to be asleep as part of their calculation because you haven't yet like incremented your counter or whatever, or decremented the number of sleeping threads counter. But all that would cause, the only thing that would do is cause them to overestimate how many sleeping threads there are, which might then lead to them searching for a sleeping thread that they never find.
I think I'm a little more wondering about the other direction, where if you get woken as a sleeping thread for available work, and then your latch is posted or near the same time.
I see.
So you might wake up for new work, but actually go process your latch instead because you also see that.
That could definitely happen, yeah. So you could be awoken for new work. Let's see, so yeah, you could be awoken for new work and then have the latch get set. And then you exit the idle loop because your latch is set and never steal. I don't think there's much mitigation against that except for this mechanism of waking another idle thread if you happen to be the last one.
Okay, so that'll still go through the last idle worker thingy?
Yes, right. Yeah, I think so. Let's verify, but I think so. Because what happens is, oopsie, whoa, how did I get wherever that is? So what happens is in that case, yeah, I will, because if you fell asleep, you're in the no work found callback. And so your idle state is still like a valid value. So then we'll come around here when we get woken up, we'll see that the latch is set. So we'll exit the while loop and we'll invoke work found, which is exactly where that code lies, basically. So it's not ideal. I mean, the last idle worker, I guess I don't have a good idea of exactly how effective it is in that, well, you might have wished that you might have another idle worker out there, and so you might not be the last one, even if you were designated to pick up that work, right? But,
I think it'll fall in the same trap of there might be slightly worse latency than we could have, but
right.
But we won't actually stall for this.
That's right. So let me talk about the logging a little. Well, we can talk about interesting races too, but I might mention the logging because it was designed to let me test some of the hypotheses around what kinds of racing might be occurring. It's not too complicated. So I added this. I don't have the measurements off the top of my head right now, but I added this log mechanism the idea is that it's very simple-minded. If it's enabled, it's going to start up a thread, which will do the actual work. So if enabled starts a thread, a logging thread, separate logging thread, and each worker thread posts events over a crossbeam channel, one of those multi-producer, multi-consumer, whatever channels. This one.
Is this per thread pool or global?
Per thread pool. I was originally going to do something much more clever where like you would accumulate threads in your local thread local state and then send, but this seemed fast enough. Like in particular, running with this enabled, at least for the benchmarks I was looking at, did not affect the throughput values. So that seemed good enough. Though I did later find other benchmarks where it did affect the throughput. So
running disabled is going to be the general case more important too, but yeah.
Right. So it's actually right now, I think it gets compiled out in the case, unless if you build release, like there's like this log enabled is a hard constant. So it'll just.
Oh, it's not an environment constant.
Well, it's like.
Oh, okay. It's compile time config. Okay.
Yeah. So that is maybe a little overly conservative in the sense that I've never seen any impact if it's not enabled, even if it's compiled in. But you know, that's how it is right now. It's kind of annoying actually, because then you can't, you have to recompile to use it. But so the point is, it sends these messages. It has a few different variants, but the interesting one was probably profile. It sounds promising. And what that tries to do is, let's see. Yeah, basically it receives these events and it simulates the state of the world at each point. So it tracks, the events might say like, I started a new thread, I terminated a thread, I posted work, my thread went to sleep, these kind of major state changes. And so it'll adjust various counters for like, okay, then it's kind of reproducing the logic, I guess. But in that case, I know how many threads were asleep at this time and I know how many were awake. And then the idea was that you can produce statistics like whenever a new job is posted, or how often does it happen that a new job is posted and no threads are idle to look for it? Or how often does it happen that, what is the average number of idle threads when a new job is posted? Things like that. And it's not 100% perfect, but this is always kind of an approximation. And I was gathering statistics like that. I think the analysis is in a different crate. But here's the simulator I'm talking about. So for each event, it just kind of adjusts the thread state. Like, okay, it was idle, now it's working, now it's terminated. And here's the local queue size. So when a job gets popped, that adjusts our local queue size. Here's the injector size. And maybe the thread went to notify. So the other thing I was curious about was like how long in between the time that a thread is woken up in the sense that its convar is notified and the time that it actually wakes up and starts to do work, is that a noticeable, like is that a long time? And the answer is sometimes.
Does this log timestamps too or not?
I did originally. I think I removed that code. Let me look. Because I found that they weren't that interesting. Like originally I was using some x86, the RDTSC instruction and logging timestamps. But in practice, the difference in the statistics when I just used the index and the vector versus the timestamp was nil. So I took it out because it's one less dependency. The actual logic does something like accumulates 100 events in a vector. Yeah, here it is. It sits there and builds up, sorry, there it is right here. It builds up a vector to capacity. If the vector gets full, then it dumps stuff into a file and then it jumps back. So I don't know how important that is, but that was the idea. That most of the time you're just pushing on a vector and then you generate a bunch of data and dump it out all at once. Hopefully after the agent, or sometimes after the agent is done. Anyway, so I did generate these statistics, and I don't recall, unfortunately, I wonder if I have my notes. I don't recall what the values were. I think I left some comments on the RSC, but we could rerun and see, and it might be interesting to test some of these hypotheses of like where time might be going. But I think my conclusion from it in the end, I couldn't find any obvious culprit, and it felt to me like what was happening was we were doing a good job of keeping idle threads, at least in the test cases that were slower. We were doing a good job of keeping idle threads awake. I'm looking for if I had any measurements, but just not as many, which is kind of what we want. Like the main difference between this and the normal Rayon was the number of idle threads in the normal Rayon was just more, which is exactly what we're trying to reduce. And you can easily imagine that if you have more threads all searching, the latency till they steal a job is going to be lower because there are more of them, and there's more likely that one will find it. They're all going round robin basically at different points. And that seemed to be what accounted for the difference. And I felt like that's kind of inherent.
They were storming every time there was a new job anywhere.
Right. It is, maximally, you're over provisioned as a certain value. I'm curious where this Rayon plot, maybe this is it. So I also was producing plots, but maybe I never pushed the code into GitHub. I should go find my old laptop. Hopefully it's not gone forever. I guess I can rewrite it. It wasn't super amazing, but it'd be annoying. It's totally plausible that I never did. I probably was living on my server that is now completely dead, which is unfortunate.
Can we take a quick break?
Yeah, sure.
Thank you.
I might take a break too.
Welcome back.
Thank you. Now I'm wondering, where did that code go?
But wait a second. This race condition means that we could have a job in multiple queues.
No. Which race condition? This last one?
Yes.
No. So what happens is the job will get pushed onto the queue of the thread that produced it. And then the question is whether that thread will wake up other threads to steal the job. And it might opt not to because it sees idle threads around. But those idle threads, what it has to sort of guesstimate is how many other jobs are getting pushed at that exact time. But in any case, the job will only get pushed into one deck, the local deck, and then can only get stolen once, no matter what happens.
Okay.
Like by some other worker, just because that's a separate atomic mechanism.
So wait a second, you can steal just once?
Any given job can either be executed at most once. Well, no, exactly once. So it could be stolen, or it could be executed by the thread that posted it, but only once.
Okay.
I'm wondering now, as we say this, if there's some way. No, I don't know how it would work. The general way to address this last race condition would have to be some, I guess, some way to estimate how many other threads are kind of measuring the overall system velocity of pushing new tasks or something and taking a guess based on that. I don't know how that would work. There might be people who try these heuristics, but I think the heuristic of checking, there was a paper I read once, I think on this topic, and the heuristic of checking your local thread queue to see if it's empty or not came from there. I can't remember what the name of the paper was, but I think their conclusion was basically that they tried a lot of complicated stuff, and this simple heuristic worked much better than all that complicated stuff. I think they called it being hungry. The thread was hungry if its local queue is empty, or the opposite, maybe. I don't know.
Which platforms have you been evaluating on?
I only ran it on my desktop, which had 24 cores or 28. No, 14 cores, 28 hyperthreads. I probably ran it on my laptop too, but that.
Are those both Linux or?
No, my laptop was a Mac. It's now I'm now running WSL on Windows. I haven't done any performance measurements on there. I still have the Mac somewhere. I could whip it out.
On the Windows one, I'm not too interested in WSL actually, because emulated kernel scheduling is going to be weird, but native Windows would be good to know.
Yeah, that I should do. I haven't set up Rust on native Windows yet, which is a sad testament to my biases. But
do you know if your WSL is the old one or the new one?
It's WSL2.
Okay. Oh, so that is actually a Linux kernel, but
I haven't tried to measure. I also was kind of skeptical of how meaningful the performance would be. It'd be better to test it on real Windows.
I know that WSL1 is weird, but yeah.
I'm trying to think. I think this covers all the major changes. There were a few other incidental refactorings, like we used to have one target latch. I made it one per thread precisely so that it had each one had a owner, like a well-known owner. Before there wasn't such a thing. That was a pretty minor thing though.
I think one thing about logging, I think we should make it clear that this is a debugging tool and not part of our semantic interface.
Yeah, I would agree with that. I think the configuration, yeah, sort of a debugging and measurement tool, not something to be relied on. Or maybe just debugging even.
I mean, I actually like clarifying for users that the semantic interface part of it, that like this is something we will feel free to change in later versions.
Yes. Well, I considered vaguely whether we would commit to the idea of there will be some tool, some flags that emit data, and there will be some other tool that can parse this data and do things with it. But I'd rather at this time I see no reason to even say that. Just say at the moment we have this available. We do not promise it will remain available or in its current form.
Right. I mean, it seems logical that we would want something available, but without committing to what exactly that is.
Right. I guess it does seem like a useful thing to be able to say, take your app, set this environment variable, and then like if you want to reason about how much parallelism you're getting, you can do it easily enough. And we have tools to help you understand the output. That seems like a cool feature. But
Right, that's kind of why I asked about the timers, because for app debugging, the timer is more useful because I care about if I have parallelism for most of the time and not so much.
Yeah, and in that case, the other thing I would say is that I'm not sure. Well, I guess in general, I don't know if what I set up here is what you would want for debugging your app. Like maybe the stuff.
I actually think not. So like it could be that we would want to limit the scope of this in that way.
Okay. Frederick Wagner's thing might be closer. Is it Frederick Wagner? Well, anyway, Wagner F. But
yeah, we currently use a thing that basically logs the start and the end of every task we have in time, which actually does let us easily, if you just like, instead of gathering stats more, like you look at it. But I can at least from I can tell you that like the multiple threads waking up idle at the same time, like never happens for our use case. We always get the right number of threads woken up.
yeah, it seemed like the main use cases that suffer. Well, they had this characteristic. It was like the quick sort and the parallel sort. Maybe they have this characteristic of just dumping a lot of jobs.
There would also need to be, I think, to have this happen, you'd actually have to dump a lot of jobs, not at the same time, but like if you
Right.
basically dumped a ton of jobs and each of those jobs dumped a ton of jobs at the same time, then as the very first thing that job did, that would be the pathological case, I think.
So
They were somewhat uneven. There wasn't like a constant stream of jobs. That would be fine, I think, because then things just won't go to sleep. But it was more that they would come in bursts and there would be enough time between them that things start to go to sleep. And then it just doesn't scale up fast enough, kind of.
the Firefox stuff might actually fit that sort of bursty profile.
It would definitely be worth measuring that. Yeah, I mean, regardless, we should measure the Firefox case.
So I guess I have if I want to go back to the sleepy state. So that heuristic where you compare the job counter to the sleepy counter, is that like the only place that's used outside of the worker, or in terms of scheduling?
Yes. It's the only. I would be happy to entertain alternative designs, but the goals there was that most of the time when you publish work, you're not doing any writes, or if there are, I shouldn't say most, but if there aren't sleepy threads, you're not doing any writes. So if you're just constantly publishing work, and the idea then is that the counters just remain equal and you just keep going. But if they are, then you do.
One thing I'm a little confused about that comparison is it makes sense to me, like the case where like, job counter is 0 and sleepy counter is 0, or that like job, sleepy counter is 0 and job counter is something, but like it also is false if like they're just mismatched, like job counter is 1 and sleepy threads is 2, and it seems to be a super rare case that would ever happen.
The jobs counter should never get higher than the sleepy counter, except for rollover, which we should discuss. But the idea is that it goes up to the sleepy counter, but never above. So there really is only kind of a binary state. It's either they're either in sync or they're not.
Would there be pretty much any cases where the job counter, so the sleepy counter, say it's there's 4 threads, and the sleepy counter is at 2, and then the jobs counter is also at 2. Is that in any way meaningful? Because then it's equal when they're both 2, and I don't see how that.
It's not. It's meaningful in that it means nobody has. It's not really counting the number of threads. It's more like a clock. So it's like 2 threads went to sleep. 2 threads got sleepy over the course of this execution, and since that, and jobs were posted at some point after that happened, after the second thread got sleepy.
Oh wait, also, I maybe missed this earlier. On the sleepy counter, does it go back down when the thread is actually asleep?
No.
Okay, that makes way more sense. Okay, I get it now. I thought it was only counted when it was sleepy and not asleep.
Yeah, it's kind of poorly named. I think it should be called a clock because it's monotonically increasing. And so I think what should happen, first of all, I should rename it. If that will help, I don't know, but yes. Two things I think I would do. First is I would rename to clock, and second is I think the procedure would be when you become sleepy, you read the counters and store the old jobs counter, increment sleepy counter, or roll over to 0 if necessary. And when you are trying to sleep, you check if the jobs counter has changed. And the reason right now we store the old sleepy counter, but the reason I make this distinction is I think for rollover it's important because you could be in a state then where like maybe the jobs counter was, I don't know how many bits we have for it, but n-1 where n is max. Or they were equal at the max value. Then you rolled over the sleepy counter. And so if a job wasn't published yet, then of course the job counter is higher, but that's not all that matters is are they equal or not. And when the job gets published, it will become equal always.
Okay.
Wait, have we talked about rollover? Because it seems like something we should be avoiding.
We didn't talk about it, but I don't think that's why I'm talking about it now, because I deferred it to come back to.
Okay.
But I think you can't avoid it because, especially in a 32-bit case, there just aren't enough bits to avoid.
So you only need number of threads, right?
But it never gets decremented. So.
Oh wait. Really?
The sleepy. There are 2 things. There's There's 2 sets of counters. The jobs and sleepy ones. Those are really clocks, not counters, meaning they never go down. They just go up. They're more like how many events happened. The other ones are tracking the number of active threads or the number of idle or sleeping threads, and those do get incremented and decremented. We could, of course, there would be other schemes that are not as tricky, but they involve writes on the common case. That's why I didn't do them. They involve atomic writes when posting work, at least as far as I can tell.
It seems like handling rollover should be doable with never having to.
Right, I don't really see a problem. It's just about if they're equal or not.
Do to rollover, like they set the numbers really high and then run it.
I don't know if I did. I should though. I think I did because I think I made the max quite low at some point just to see what would happen. But it would be worth testing it explicitly, maybe making a test for it. But yeah, the important thing would be that they're just equal or not equal. So also there's two important things, I think. One is that the number of threads, you don't want it to loop around. So there's a max on how many events can occur without a job being posted, which is all the threads might get sleepy. And that means you need at least as many bits as you have threads, I guess. But as long as you have enough, it should be okay.
So we should document that max though, especially if we limit 32-bit to, I guess, 256 or maybe slightly less threads.
Yeah, otherwise, well, actually, what happens? I think it even may not be the end of the world otherwise. Like, if it were too few, I think it just means you'll sleep one more. You'll think that a job was posted and you'll go one more round. But I would want to. In other words, the thread that becomes sleepy then sees that, okay, now then when it comes to go to sleep, it says, oh, the jobs is equal to my sleepy counter. Well, I'm not sure. I guess it
Well,
depends on the
things like-
details. But
Things like the idle counter or the sleeping counter. If you, I don't think you can do that modulo 256 or a smaller number of bits, because you could end up on a 0 when there's actually a lot of threads sleeping.
But it's not counting how many are sleeping, right? It's counting how
not?
many. It's only counting how. It's counting how many went to sleep since rollover.
So things like last idle, assume you have an actual number, knowing how many are idle.
Yes, that's right. But
Isn't that
that's the two different things. So maybe we need a different name. Clearly, these names are confusing.
okay?
But there's what I had called the jobs and sleepy counter, and then there's the number of threads and the sleeping threads, and these are exact.
So those two numbers need to have enough room to not overflow.
Yeah, these cannot overflow. This one I expect overflow will
If you
happen.
rename them, like just even putting like say the sleepy event counter would be much clearer.
Yeah.
Say it's an event counter rather than a thread counter or something.
Let's do that down here so I remember to do it. I will, yeah, and we should write out exactly what happens with rollover, but I think it would work. It might be. I'm gonna have to go and. Oh no, I don't have to go. Not yet. If we had 32 bits, we can loop back to that for a second. If we have 32 bits, I guess if we impose, you could imagine imposing a limit like 128 worker threads or something, which is still quite a lot, probably.
64-bit will have a limit too, 16 32K.
Right. The current code has 2 to the 16, so sorry, my branch has this limit in practice. I don't know what if the current. I don't think the existing it had some limit. I mean, in practice, because they have thread IDs, but like it's a pretty big one.
Yeah, I think we had usize max or something at least, but.
But it seemed to me like 2 to the 16 was a pretty reasonable. I doubt it's going to scale that well up to that many threads anyway. So.
Do you error over that or just cap it?
I don't know. I think I don't even detect it. I just assumed it. We should probably add something. I would probably just cap it. I don't know. Well, in any case, if you had 32-bit, you could have 8 bits for a jobs event counter, 8 bits for a sleepy event counter, 8 bits for idle threads, and 8 bits for sleeping threads. What I don't know is if there is indeed a problem, I have to think about it, for having the same, like if you want to have the event counter able to be incremented by every thread and not overflow, it might be that this has to be 7 bits, or like maybe not have to be 7 bits, but that the actual limit is not 2 to the 8, but 2 to the 8 minus 1 or something. If you see my point.
Yeah.
I'll move that down to the bottom. That's still quite a lot of threads.
Especially on a 32-bit platform, yes.
Right. It seems unlikely that 254 threads is all that useful right now. It could also, yeah. I was thinking that it would be plausible to do a swap out more like, I think the counter mechanism is, it's probably not completely encapsulated, but could be encapsulated to a certain extent, such that you could have a different mechanism. You could do different things on 32 versus 64-bit if we found that the limits were problematic. That might be somewhat slower, but like involve more communication.
I think there's a limit to what sort of effort is worth applying to 32-bit targets right now.
Yes, I agree.
So, or if people care more about 32-bit, they can come and help us do that work. But
right.
As long as we do something reasonable, I think we're okay.
So I couldn't find any. I was hoping that reading through the code, I would see a bug that might lead to seg faults. I did not.
Are you even modifying any unsafe code here?
Well, that's not. I mean, the Rayon core is like the unsafe part of Rayon.
Well, yes, but the unsafe stuff has to do like lifetime erasure and type erasure and things like that.
Yeah,
I think you're really.
I didn't modify any code of that kind. But I could imagine there being a seg fault if, well, for example, if we got the latches wrong so that things started to execute when they hadn't actually happened, or.
But you were doing, even your atomics, you were doing like seg CST and a lot of them, right?
I was. That was another thing I wanted to check. I mean, it might. If I could reproduce it, I'd love to. You know, it'd be a little easier to test. There is this one thing that always bothers me about the C++11 memory model that I wanted to double check before we got on this call, but I failed to do so. About the interaction of sequentially consistent operations with other kinds of operations, and how much. I'm trying to remember the details of the case that frightened me, but I think it seems like there's some additional ordering that's imposed on sequentially consistent operations, and the question is how much that applies transitively. Like, is it possible to have an acquire-release relation within one thread, something that would have propagated to that thread via acquire-release, and then a sequentially consistent operation that synchronizes with another thread? Is this other thread guaranteed to see thread A as a acquire-release relationship to thread B, and then thread B as a sequentially consistent relationship with thread C? Does thread C see the writes from A? I think that's the case I'm usually concerned about. And I sort of forget the answer. But I do remember I loosened a few things in the Latch code to acquire release from sequentially consistent after convincing myself that it was correct. And maybe I was wrong. Latches seem like the poster child for acquire release, but they're like a one-way communication.
Yeah.
Although when I look at the code here, No, I am doing acquire release here and set, I guess. But some other places I'm doing sequential. I'm a little inconsistent. Maybe I was just. Anyway, I mean, I could just change it all sequentially consistent, see what happens. if
Well,
Wagner can reproduce it, it'll be good.
if you can't reproduce it, then seeing what happens is not very helpful. But
Yeah, no. I didn't see any crash on my system though. I do remember seeing one at some point in the Git history, and I fixed a bug and it went away. But maybe I didn't really fix the bug that I thought I did. But I can't reproduce it now, so it seems unlikely because it was happening pretty reliably.
well, seg faults are nasty too, because you could still have the memory issue without causing a seg fault.
Right.
Valgrind's too darn slow and messes with all this stuff anyway. Although I kind of wonder if we're, now that we're not doing the job storm, if the behavior in the Valgrind will be a little nicer.
Well, possibly. I also wonder about plugging in Loom and see what we see, but I have no idea how that would work. I haven't really looked. It's not like super simple to do, I don't think.
No, you kind of have to mock out interfaces, and
yeah,
it looks like a cool library, but not something you can just plug and play. And then Miri would be nice too, but I think it just doesn't support threading at all yet.
No. So what do we need to do to land this? I got 30 minutes.
Yeah.
Assuming you're still feeling keen on landing it.
Yeah. So addressing the 32-bit stuff matters. And then definitely adding some of the knowledge that's in this document as code comments.
Right. Code comments, maybe update the RFC as well. I would find that helpful in the sense that it is long form, but also the act of writing tends to force me to think through things that I might have been a little blasé about beforehand.
Sure.
This seems all doable. I don't know, Luca and Thomas, how much you all are interested in, like, I'm slow.
Okay.
It might
So,
be nice
I mean,
to collaborate.
we tried it quite a bit, and for our use case, it's working really well. So we have this kind of problem.
Okay.
Yeah. So I mean, is there a part that what part do you want me to take here, basically?
That's what I'm wondering. So, I mean, one thing might be like the 32-bit. It's not super hard, but in theory, but it's code.
Compile time, changing that type, and then setting the. I guess besides compile time, changing the type, it's mostly I guess the tests that needed to be there anyway, but are more likely to overflow now.
Yeah. Is there an easy way to config whether you're on 32-bit or 64?
So I suggested above that we can just change it to atomic U size, and you'll get the 3264.
That's not enough though, because we need to assign the bits inside of it for.
Yeah. So you can use target pointer width, config target pointer width,
Oh, okay, good.
and just choose 32-bit and 64-bit values.
Yeah, we need to compile the shifts and all that annoying stuff.
It'll be an annoying block of configs, but we could even use config if you want.
Probably it's just a matter of tweaking the constants, or if it's not.
I mean,
we need more constants.
this atomic type has getters and setters, so it's like only going to be inside that.
Right. I tried to encapsulate that logic, so that helps.
For the seg fault thing, there might be some like malloc tuning options where we can tell malloc, or even like glibc malloc, or maybe switch to je malloc for testing to set more aggressive freeing options. I mean, if you can get malloc to discard pages that have been freed, it might give us a better chance of hitting the real segfault.
Yeah. Or like, people still use electric fence, something like that. I guess valid,
Yeah.
right? I guess the first thing would be to or maybe we can like get a, I don't know, a login on a system where it reproduces more readily.
Who reported that?
I think Wagner did. He says, I guess that's another question. Can you go find the code for Rayon plot? Would be nice. I learned SVG for that. Was emitting SVG directly.
Wow.
Yeah, okay. We'll just have to see if we can reproduce. If we can't reproduce, oh well. We'll pretend it doesn't exist until somebody reports it.
So I realize I have one question that's not quite related to this particular branch. It's just that with the sleepy state of the worker, you mentioned so basically like loops. I think it's set to like 32 times for a spin lock. Like the only purpose of that state is a spin lock. You need to increase the event counter right when you start wanting to do this spin lock and then the sleep. So that's the only way that's really visible.
Okay, sorry. That reminds me. I'm not sure exactly what you're saying, but I would point out that I totally changed these constants also. I think they're much smaller now than they were before. But
Yeah, so it's like the one thing I noticed when I looked at the loop is it's like it's calling the scheduler yield function every time through the spin lock. And if that actually like context switches, it would be basically as far as I know the same cost as actually just sleeping.
Yeah, this kind of came up in that recent storm about spin locks versus mutexes, where Torvalds got involved. That Linus kind of made a statement that if you're calling sched yield, you're probably not being as effective as you think you are. So, it might be worth just forgetting rounds here and just make it like a one-step transition from sleepy to sleeping.
Yeah, or potentially do a loop that doesn't call yield at all. But I'm not sure if then the sleepy time is going to be so short. But I think I don't know how long the sleepy event is before it sleeps in terms of like microseconds.
not very long. The current one, at least, I have it tuned to just one round.
Okay.
I think I tried other variations and it didn't make that much difference, but well, that's actually not entirely true. As I recall, for the benchmarks that we were seeing performance effects on, it did matter somewhat because they were basically the more time it's kind of directly proportional. The more time your thread spent searching around, the better the results were.
Yeah, that one thing the one other issue I noticed is that we've with at least master branch, which we'll see if this affects I haven't really tried this a whole lot with it already helps with the latch target thread branch, but with our software, it by default chooses a number of threads equal to the number of CPUs. But if you were to run like 2 instances of a program, then you have of course allocated twice as many threads. So there could be potentially bad behavior than if you're trying to do the spin lock, but you like you yield and you're like yielding between 2 threads that are both spin locking. It's kind of really bad, and it could make the sleepy state last a lot longer than you'd otherwise would. So that's like a case that's not addressed by any of the tests right now. And so, we've been able to solve it because like when we set it up, we always make sure to configure each of our, if we run multiple instances of a program, we set each one to have a subset of the number of threads of the CPU. But it would be nice if it didn't, have bad behavior in that case.
I'm not entirely sure why. I think I just put in yield now because I don't know. Just because I'm not sure that was a correct decision.
But yeah, that's kind of separate to the branch. I just thought I'd mention it in case there was any insight there.
Now I'm trying to think how important is the sleepy state at all? But I feel like I can't. My brain does not want to turn on right now.
Well, I think you wanted at least, I think there was a reason we needed a sleepy state to get the synchronization right. I don't know if we need 32 rounds.
Well, I think you need the sleepy state because you want to increase that. You at least want to increase the event counter the moment you do any check on the lock, and not before you grab the final sleep lock.
Right. So one function of it is to create this period of lightweight wake up, right? Where we wake up, we notice the work in a lighter weight way than having to go through all the work of.
Yeah, potentially, I guess if you only have one pass through there before if it's like part of the sleep thing, you could remove the state or just have the state be exactly one check without the loop, which is the thing I'm not going to work on that first because I think I would rather work on improving the counter situation for 32-bit to get this branch done. That's one thing I might also try benchmarking is dropping that down. And I'm sure it's strongly dependent on what your particular OS's yield thread function does also.
I think the other reason we needed sleepy is that if I recall, we were limiting so that only one thread would go into that, would make that sleepy to sleeping transition at a time.
Oh, in the older code, yeah.
Is that not true now anymore?
No, not anymore. You can as many as you want.
Okay.
Yeah.
Well, I think that was the reason why we had it before, was because they were basically serialized to transition to sleeping.
Right. And I was trying there to solve a bunch of random things, but among them, I didn't want to have any limits on how many threads you could have and stuff like that. Doesn't make any sense. But
maybe that's something I'll revisit after we get this landed.
No, but one of my big goals was definitely that many threads the threads are acting more independently in this branch, and they're not serialized to go to sleep one at a time.
Okay. So yeah, I think generally I'm happy with the tour I've gotten here. I haven't done the actual code review comparing side by side what the actual changes are. I'm basing this based on what you've shown me. So I don't expect surprises because you're an honest developer, but we'll see to compare.
I could overlook them.
Yeah.
So maybe what I'll actually do is I'll take this branch and I'll make a PR right now that I'll like pull the logging all out and take all of the undo redo patches out, and I'll make a PR, and then I'll start stacking the atomic theory too.
I think I already did that actually. If you look at the branch, the number 2 branch, Latch target thread 2, the commit history is, how do you get a nice, I guess this button?
Oh, I see. You're now 6 commits ahead, so that's way better.
Yeah. I put the logging in one place, but there's like some commit at the end that's just kind of do all the rest. I couldn't cleanly separate it out, but I guess it's this one, add new thread pool.
Yeah, I think it's going to be like that just because
right.
You can't change half the thread pool at the time.
Right. It didn't seem like it was, and sometimes even if you can, I don't personally find it easier to read if the same code is changing again and again and again versus just jumping to the final state.
Certainly if any tests fail in the middle states, it's really irritating.
All right, well, let's discuss on Gitter, I guess, but I think trying to get the 32-bit in there and moving some of the the first most immediate step is I'll try to move comments in. I'm happy if other people want to do it too. By the way, I can add you as a collaborator, so you don't have to make PRs. And I guess we're going to try to land it on master, right? And just, we were discussing about the idea of landing it on master and calling for people to test it and see if they can hit any problems.
Yeah.
Another option could be, if we have the ability, is to run, run a whole creator for just stuff that depends on Rayon. That would be possible.
Can we do creator that patches the Rayon version? Is that,
Yeah,
does creator do that?
I don't know if the whole machinery is able to do that, but that should help us to see if at least automate the process. Otherwise, calling for feedback probably would be the other easy solution.
At least testing with the Firefox code is a good idea.
Yeah, if we could like bump the version in nightly, it would be pretty cool.
I didn't quite understand that last part, but
If we could run it in Firefox nightly, the
okay.
version. I'm not sure if that's too much. People may not like that.
I think we could do a local, at some point, Bobby Holly posted on our wiki or something, instructions for how to run the test locally at least.
Yeah. So one of the things that what I remember of his testing was that he seemed to be measuring things like how often do they get cache hits, which is a very high level metric of performance for them. And I don't expect any of that to be very much affected by what we have here. So I think we actually care about raw performance numbers, real timing as an effect of this branch.
Do you have access, Josh, to like interesting hardware that we could test on? If we had like a standard test.
Yeah, maybe.
I wonder if Josh Triplet does.
Well, and we have a Beaker lab, which has all kinds of interesting machines, but the really fun ones are often in use.
But also, like, I guess now that I think about it, we should test on crazy machines, but the most relevant is probably smaller. I don't know how many people are using Rayon with massive, unconventional setups.
Right.
All right. An open question about what to do when and if we notice that we are in an overcommit state.
Sorry, what?
You mean with multiple, more threads and CPU cores?
Yes.
Or multiple? I mean, there's no way for us to detect that in the sense that like we can't detect other thread pools from other Rayon. So I think it's something that I would just test. I mean, write maybe a test for it and then see if I can change stuff and makes that case better. But there's no way to detect it as far as I know. It would be out of scope of Rayon, I think.
I think it's out of scope for this branch at minimum. There is some kind of it would be interesting to talk about at some other point. There's some people who explored architectures where they can like make changes of this kind, but it would require a lot of work where they can detect if they're kind of grow and shrink the number of worker threads.
I should, while we're talking about interesting machines, I should try some other architectures too. Like I can get this running on S390 or PowerPC pretty easily.
Yeah, me and Luca both have a Power 9 box under our desk, so.
That would be good.
ARM is probably a more important target, which I do have as well. 32-bit ARM is another one of those cases where we only have the atomic U32.
All right. Cool. I will try to motivate myself to do some of this too. I've been very, I don't know. I've just been wanting to lie around the couch. I'm not working right now, which is not a bad thing. But
Well, I'll always poke you for patch reviews.
yes, at least that I can do. Thanks, everybody. I guess I'll call it
Thank you.
close.
Thank you. That was great.